my first slide. It's a little bit funny. This is here reading tea leaves, okay? It's a powder, of course, and reading tea leaves, the story behind this, I was once introduced as a speaker at our Max Planck Institute by our technical director saying, oh my God, structure determination from powders is like reading tea leaves. So, well, yeah, not really. There is a lot of science behind, and this is what I'm going to show to you. Source of information for this talk. So the main source are the two books here. The first is Powder Diffraction Theory and Practice. This is the version from 2008. It's so Simon Billinge and I are the editors of this book. It's a textbook on powder diffraction, and there's even, as you can see, there's a Chinese version of it. Believe it or not, I mean, they took the book and they copied it one to one, even translating all the figures and stuff. But you see, 2008 is a long time ago. Science is moving fast, so there will be a new version, which will be edited by Max Turben, who is sitting back there, Simon Billinge and myself, and we hope, so keep fingers crossed, that by the end of the year, this will be out. It's a really, I can say it's a brand new version, so I would estimate that at least 60% are different of the book. And then there's another book here I wrote together with Andreas Leinerweber and John Evans about Rietveld refinement, in particular for topaz. So all the exercises, all the demonstrations are basically from these books. And as Paolo mentioned this morning, Paolo Scardi and I, we wrote two educational papers, Powder Diffraction Education, in the Journal of Applied Crystallography, one about the peak profile and one about the intensity of a Bragg peak. And the interesting part of these papers is that they contain, I mean, not the papers, but you can download free Mathematica scripts where all the things which are explained in the papers they can try out. So you have this special feature in Mathematica with sliders and stuff, so you can change things. You have seen one of the scripts actually by Paolo this morning, yeah, where he showed how to transfer the scattering to the TDS. Okay, let's move on. And this is my favorite transparency. It's already in all of the books. It's just giving you a glimpse of what information actually is in the powder pattern. And this is a very schematic thing. Yeah. So of course we have the background. We heard a lot about background today. Most people want to get rid of it. Yeah, and which is perfectly understandable. But if we have a chance, let's say, for example, if you go far out in Q space, if you do the total scattering approach, if you look at PDF, then there's a lot of information in the diffuse scattering. Yeah, I mean, everything is elastic, but there's Bragg scattering and diffuse scattering, and usually you forget about diffuse scattering. But there's a lot of information. But of course, you have to distinguish between what's coming from the sample holder and from the instrument, and of course the inelastic scattering, mainly Compton or fluorescence or stuff, from the sample. So there's a lot of information, but here we are not talking about this, and Max will say a lot more about this in 2 days. Then we have the reflections, and of course the very schematic scheme is we have position. We learned today, this gives us lattice parameter, space group. We can learn about macro strain, yeah, if peaks are shifting because of strain, qualitative phase analysis. Then we have the crystal structure. It's what we are interested in today because we want to solve crystal structures from powders. So the atomic positions, if you do neutron diffraction, you can get kinetic moments. You get, it's actually the wrong word, temperature factor, it's not temperature, it's Debye-Waller factor, yeah, or displacement parameter. Occupancy, information about texture, and quantitative phase analysis. And last but not least, the profile. And there it's very, very important, as Paolo pointed out this morning, if you want to learn from the profile of a powder peak, you have to get rid of everything which is coming from the instrument. So you have to determine the instrumental resolution function. And more importantly, this has to be deconvoluted from the actual powder pattern. Yeah, so there must be a deconvolution process. We will talk about this in a second in greater detail. And with what's left, yeah, there's a lot of information about the microstructure, and the microstructure for us generally means this is the domain size, so this is the size of coherently scattering domains. It's the microstructure, which is a cumulative term, basically a measure for the defects in the material. And if you do more and more advanced methods, which is possible nowadays, you get a lot of information about stacking fault disorder, which is not topic of this workshop. Yeah, this is shown very, very specialized. You have seen this formula already. It's a little bit written a little bit differently, but we are talking about powder pattern refinement, or basically Rietveld refinement, and so we have to talk a little bit about the idea Hugo Rietveld had. It was not only him, but he was, I would say, he was the main figure, and he wrote the most important papers on this. To give you an idea about time, I mean, the first paper which you could call Rietveld refinement came out in 1966, and then he presented the method in 1967 at the IOCR meeting in Moscow, and guess what? Nobody was interested. And he was a clever guy, a really, really nice and clever guy, and he figured out if you want to make something popular among scientists, even at that time, you have to distribute a working program. So when he came back for the next 2 years, he was sitting down in Algol. I think this is a forgotten computer language, yeah. Later than Fortran 77, but at the beginning it was Algol. He wrote an Algol program, and he put it on these big magnetic tapes. And he was sending it out to everybody who was interested, and people figured out, oh, this is a great method. We want to have it. And this is how the whole thing started. And the idea is very simple. I mean, instead of extracting single intensities from peaks and using the well-known single crystal methods, yeah, which works in cases where you have well distinct peaks in the powder pattern, he said, hey, the best would be if we actually have a function which models the entire powder pattern. The entire powder pattern consists of the peak positions, of the peaks, of the background, of everything, yeah, and to do a model as good as possible, and then use the least squares method, so minimizing the differences between the calculated powder pattern and the measured, at every single point. This is the important part, not for the peaks alone, but at every single point in the powder pattern. And this idea intrinsically yeah, takes the peak overlap into account. Yeah. It gets the maximum information from overlapping peaks. Because if you have two peaks which are well separated, fine, you have two intensities. If the peaks are 50% overlapping, you still can get good intensities if you have a very well physical-based peak model. If they're overlapping more and more, you have less and less information, and this information is, but there is still information. It's not that it's only a single count information piece. Yeah? So there is information, even strong overlap, if it's not 100%. And to get most of it out, you can use the Rietveld method by minimizing here the difference between the calculated powder pattern at each point minus the observed one. And then, of course, if you sum this up, it would give us 0, right? So it doesn't make any sense. So you only want absolute values. So you can either use the modulus, or what people in these squares do, they square it. But when you square it, yeah, and you don't do anything with the data, it will also not really work. Just imagine the case you have one big peak at the beginning of a powder pattern, and then a couple of ripples back there, and then the one big peak is well fitted, but the ripples are fitted terribly, but then still the square sum of the differences would be pretty good. It would give you a very good number. So that means you have to weigh, yeah, the intensity, so that the strong peaks are not so strong going into this equation anymore. Yeah, so a typical weight is 1 over the square root of the intensity if it follows Poisson statistics. The whole thing is minimized, and this is a procedure we talk about in a second. You've seen this figure from Paolo in the morning. This is just a very schematic thing about the Rietveld's formula. And you see this is the formula, and it's actually a very simple formula if you do it as a scheme. So what do we have here? We have here a double sum. The outer sum, yeah, the outer sum goes over all phases which are present in your powder pattern. Yeah? And what we are calculating actually is one single intensity in your powder pattern. So if you have 10,000 points in a powder pattern, it starts from 0 to 9,999, okay? So at any position, yeah, you have to figure out, or the program has to figure out how many phases actually contribute to this position. And that's actually an important question. So in theory, you can say, okay, all phases contribute to all points in the powder pattern, but then the calculation is just too much. So you have to find a measure how far out you calculate a peak, okay? And the typical thing what you nowadays do, which is very well accepted, is that you calculate the peaks as far as once they are 1/10,000th of the peak maximum. Yeah? If it falls below that, we stop. Okay? So Rietveld programs actually have to make these lists. We come to this later. So it goes over all phases, and then of course the phases have a certain quantity. So we have a scale factor. So this is this scale factor here. For each phase there's a scale factor. And this scale factor is directly related to the quantitative phase analysis, and I think Arndt will say a lot about this scale factor day after tomorrow or tomorrow. Then we have the peak intensity in here. This is the peak intensity of a particular reflection, HKL, of a particular phase, yeah, which is contributing to this particular point I here in the powder pattern, the peak intensity. And then the peak intensity is multiplied by the shape of the peak. And this is actually the big difference to single crystals and powder. If you have a single crystal, you're not so much interested in the shape of your peaks. You want to integrate, yeah, your spot. Yeah, so you can live with a relatively simple model, actually peak model. In powder diffraction, it's very important, particularly if you have overlapping peaks. The peak must be perfectly described. Yeah? If it's not perfectly described, if you just say, oh, we do these squares, let's see whatever fits in, yeah, then the intensities will not be equally correctly distributed. So you have to build up your peak, yeah, from principles, yeah, from fundamental parameters. Or you have to have, let's say, working model, as Paolo mentioned today in the morning. He said you have to have some phenomenological model. Phenomenological means it works. It's not physically based, but it works, okay? So you need a very good peak model, and all these peaks must be normalized to 1, of course. You do not want intensity when you sum up the peak, yeah? If you just sum up the peak as it is, it should sum up to 1, and then this is multiplied, of course, by the intensity of the peak. So normalized models, and then you have a lot of correction functions. We talk about some of these, yeah, which is actually the crucial part in the Rietveld analysis. You have to think carefully what correction factors you will apply, or you have to apply. A couple of these are geometrical, so we have to apply them. Others are actually facultative, so they're optional. Yeah, you can say, maybe there's extinction, maybe there's this type of absorption, maybe there's this, maybe there's that, yeah. There are, of course, rules for this, and we'll look at some of these. Yeah, and then the double sum is closed, and then this is the background, and as I said, in Rietveld refinement, we don't really care about the background very much, so what we usually do is we use just a polynomial of some order, yeah. So we hope to find a polynomial where the coefficients are not so much correlated. Usually these are Chebyshev polynomials, still correlated, but they should behave in a smooth way. Yeah, so you don't want any strange features in the background. Or you can put in broad peaks as a background. Yeah? It's also perfectly legitimate. Okay, the same figure again, also as a scheme, no? Just to tell you again, I mean, this part here is actually the crystal structure, what we want to refine. This part here, the 2 theta HKL of the phase P, yeah. This is the position which comes from the unit cell and space group. The scale factor here is a quantitative phase analysis. The peak profile tells us a lot about the instrumental resolution function, the microstructure, if we do it right, yeah. And the background, if we want to do this local order, and of course comes from an instrument, but usually you forget about this. But now comes the tricky part. Now this actually sounds great. So, oh, easy. Yeah. What's the idea of least square? Or what are the limitations? And when you see this figure here, that gives you some idea. And usually when I tell students in the first semester, then you do some crystallography or then they're in contact with Rietveld refinement, I tell them, look, just imagine the following. Just imagine you have only 2 parameters. No? The typical Rietveld refinement, we have typically between 20 and 50 is a typical number. Yeah, could be many more, could be a few less. Yeah, so that means our surface is a hypersurface. So we can call it an energy landscape. If we minimize something, we want to find the minimum. If we call this an energy, we want to find the minimum energy, the best agreement. If you just have 2 parameters, you could imagine that this is the surface of the Earth, right? Surface of the Earth is 2-dimensional. And now basically you start at some nice peak in the Himalaya, yeah, which is, let's say, 6,000 or 7,000 meters high. This is where your parameters start, yeah, because you have to have starting parameters. So Rietveld is not a global optimization method. You have to be reasonably close to the correct numbers. Yeah? Global optimization, we talk about later, is a different story. But so you have to be reasonably close. But let's assume we start in the Himalaya, we are 6,000 meter high, and we want to find the minimum on the Earth's surface. And as far as I know, I think this is the border between Israel and Jordan. It's minus 430 meters down. Yeah? So we want to go there. But the only tool you get is some binocular. Okay? That's all you get. And you hope it's not very foggy. Yeah, so you're standing up there in the Himalaya, and then you look around and say, okay, yeah, there it goes down to the next valley. And so you take your rucksack, you walk down the valley, and you walk and walk and walk. And if you're very lucky, there's a river. The river goes to a bigger river. The bigger river goes to the ocean. Now you're in the ocean. And now you're swimming on the ocean. You have a problem actually finding the Dead Sea in Israel, right? Because it's completely shallow and flat. Yeah? Another possibility is you walk down, you end up in the valley, which is dead end, and you see, oh, there's the next mountain. Yeah, in the global optimization thing, you would jump over this mountain. Yeah, in the local optimization, you're trapped. That means you have the only thing you can see, your parameter space, yeah, or what your parameter sees, your 20 parameters you have. Yeah, you only see a little bit around the parameter if it goes down or if it goes up, and of course you go down. Yeah, and the reason why this is because the Rietveld formula is not it's not an how's it called? It's no algebraic formula. Yeah, it's a very complex transcendental function which goes over pages, and therefore we have to use a Taylor series expansion. Yeah, and the Taylor series expansion, which is shown here, yeah, you usually stop after the first or the second term, and that means if you have a parameter p1, yeah, you only look a little bit around this parameter. Yeah, just imagine the Earth. You're on the Himalaya. You're on one of the mountains, and you see maybe 50 meters in all directions, and you hope somewhere it goes down. Yeah, some parameters are easy because they're linear. They go down like hell, and they end up in the minimum. Most parameters are highly complex, like the surface of the Earth. This makes Rietveld refinement challenging. Okay. Agreement factors. I don't want to say too much about this. Paolo already told you a lot about it, and you see the typical factors are you have to find a measure of how good is your refinement. Yeah, and one possibility, of course, is visual. So you look at the refinement. The other possibility, you need some agreement factors. And the typical agreement factor is a profile, RP, profile factor. And that means you just take the modulus of the y-ops I minus y-calc I, you sum them all up, and you normalize it by the sum of the y-ops. And you see immediately, okay, Paolo put up the warning finger and said, now imagine your background is that high and you have a little peak up there, yeah, you get a beautiful fit. A beautiful agreement factor, but a terrible fit. Yeah. So the better way is, this is of course not the perfect way to doing it. Yeah. But the better way is of course to subtract the backgrounds first, and this is on the right side here. But again, this does not account for the weight function. So it's better actually to weigh yeah, to weigh your difference, use the WI, and the WI, as we learned, is y over the variance, no? The sigma y ops of I squared. No? And then there's something, now we can say, okay, now I have some nice numbers, and everybody likes to report them, because usually you end up at some point with a good number. But RP and RWP, no matter if you subtract the background first or if you don't do it, these are house numbers. They just give you a relative feeling of the improvement of your refinement. These are no absolute numbers. You can have excellent data with a very high RWP, yeah, it's a pure statistical thing, and you can have poor data with wonderful RWP, yeah, and it doesn't tell you anything. So people love to report the values and say, oh, my refinement is great because my RWP is 2%. Yeah, but that doesn't mean much. What means a lot more is if you say, okay, what's the best RWP I could get? This is actually the fluctuations of my signal, right? Yeah. So I can calculate this, and this is the expected R value, which is here. So M is the number of observation minus the parameters, and it gives you a number, and this is the theoretical best number you can get with your particular data set. Let's assume the REXP is 10%, yeah, and your RWP is 20, and then you can say, okay, the relation between the 20 and the 10, yeah, this gives me my so-called chi-squared. And this is a value which really tells you something about how good your refinement is with respect to the quality of your data. Yeah, so this number should be reported, but most people don't like to report it because usually it's too high. Yeah, and this is and then they look, so students come and say, look at all the other papers we're not reporting, and you say, please put this number in. Yeah, I always have these fights. No? Okay, and then of course there's something like the R-Bragg value, which is not a real R-Bragg value, but it mimics as good as possible the one from single crystals, and therefore these two should be at least reported. Usually the R-Bragg from powders is too good compared to single crystals. Yeah, it's usually a factor of 1.5, 2 better than it should be. Anyway, just remember there are lots of agreement factors. They are all valuable. They are all good, but they have to be, yeah, handled with care. Let's look a little bit about the information loss in the powder pattern. It's a very interesting paper by Bill David, Ken Shanklin, Lynn McCusker, and Christian Berlocher in 2006 in their book on structured detonation from powder diffraction data. Still a very up-to-date book. The idea is the following. So what we did here, we applied their formulas in a way that we say, okay, is there any compound which is triclinic and has exactly a volume of 1,000 cubic angstrom? Yeah, and so we found this. And now we look actually at the number of peaks per unit, and we decided to have a unit of 0.1 as you call it, a slice of 0.1 degree to theta for kappa k alpha radiation. And now we look at how many peaks are actually in this slice of 0.1 degrees. And you see, wow, at the beginning it's not that many, but if you reach 60 or 80 degrees, yeah, we have in this small area, we have something like 6 to 8 peaks, Bragg peaks in there. And it tells you immediately, now everything depends on your resolution. Yeah? If your resolution is bad, you have no idea to distinguish these peaks. Yeah? So the next little figure here on the right side is actually showing exactly this for this particular example. It says, okay, when you have a single crystal, yeah, how many independent reflections you can get out of your powder pattern, and in this case, if it's 1,000 cubic angstrom, and you see when we measure up to, let's say, 100 degrees to theta, I have to see, we end up getting something like 2,500 independent reflections. That's a great number. It's easy to solve the structure. If we have a powder, yeah, and now we are talking about a perfect powder. We are talking about a powder which is not changed by its microstructure. Yeah, actually, such a good powder, usually you don't need a powder, right? If you have a powder like this, you can do single crystal diffraction because it's so highly crystalline. Yeah, But let's assume just to show this, and you see the solid curve down there. Yeah, this is a typical powder that with the best resolution you get in a laboratory, which is a delta D over D of about 10 to the minus 3. This is state of the art in the laboratory. And you see there's a huge difference, of course, to the single crystal. It's very similar up to 40 degrees to theta, but then the curves they are complete diverging. It's, of course, if you go to the synchrotron, much, much better. Delta D over D, we reach 10 to the minus 4. It's 1 order of magnitude better. And this is actually coming pretty close, up to 80 degrees, pretty close to what we can get from single crystals. Yeah. But again, this means a perfect powder, right? And if you have, let's call it a shitty powder, so the typical powder which ends up on your desk, yeah, then there's no point going to the synchrotron, yeah, because you cannot improve resolution, because the main resolution or the main broadening is from your sample and not from the instrument. Yeah. But typically for pharmaceutical samples, for example, it's a wonderful idea to go to the synchrotron, because usually they're nicely crystalline and still can be available only as a powder. Okay, now I told you it's my bad job to do some torture. This is my absolute belief. I always tell my students, if you do powder diffraction, if you do crystallography, you have to remember what Fourier transformation is. Yeah, we are not going through the theory of Fourier transformation here, but I just tell you, if you want to understand how things work, you have to understand what a Fourier transformation does. Yeah? Just imagine diffraction is a Fourier transformation. Yeah? And it works wonderfully well if you have the structure and do your Fourier transformation and get the powder peaks or the single crystal reflections. Yeah? This works easy. The other way back is the one which is problematic. Yeah? For various reasons we talk about this. And this is the formula here from the Fourier function using Euler identity, actually from the E to the IBSX. S is the reciprocal variable, X is the direct space variable, and we use, of course, the Euler identity with a cosine and I times the sine. And the crystallographers, of course, love the repeating interval as 0 to 2 pi, because it's a wave, it's a diffracted wave, yeah, and therefore the formulas get a little bit easier, and this is the one we have down here, and you probably all recognize here that this is our structure factor, right? I mean, Osana was showing the structure factor this morning, and this is actually the, if we say for a moment this should be the structure factor, this is the integral minus infinity plus infinity, yeah, of the scattering power of x, basically the electron density, times E to 2 pi I as x dx, and the other way around. So if we do powder diffraction, or if we do crystallography, we have to understand what Fourier transformation and back transformation does. Just to remind you, it's only a transformation, so you're not increasing the knowledge, you're not increasing the information content. Yeah, it's just one space and the other space. Fourier space is our diffraction space, yeah, and the normal space is the space of our, if we have X-rays, of our electron density, okay? But we need the Fourier transformation in many, many other things, and we mainly need it in terms of convolution, because all we do in a powder pattern, everything in the powder pattern in the profile is convoluted, yeah? Convoluted means, convolution means it's a blending of functions, yeah? Here you see this typical example. You have a rectangular function which is red, and then you have, so we keep this one fixed, and then we have the triangular function which is blue, and so the integral basically means shifting the two functions over each other, so one is fixed, the other one is moving, and then integrating at every single point, and what comes out is finally this green function which looks like a Gaussian function. And if you remember your first or second math course, they probably told you, oh, if you have a rectangular function, and if you convolute it with itself at least 4 or 5 times, you get a perfect Gaussian function, okay? Yeah, so, and this is a typical example, for example, if you have if you have a photometer, right? So you have the slit is rectangular, and then you have your let's say this is a triangular, more or less triangular peak, or let's say you have a Gaussian peak and you move it over, then these two functions are blended, yeah, they are convoluted, which usually means this, if the slit is open, yeah, the whole thing gets broader, yeah. And the functions are given here, and it looks very easy. It says the convolution function is just the integral of these two functions f and g, yeah, and the whole thing is denoted by this little circle here. And if we have the correlation function, instead of a minus here, it's a plus. And if you have autocorrelation functions, of course, then the g here is actually a second f. So far, so good. But that means this is a very complex integral. And that's a big problem to do it, yeah? I mean, solving such an integral only is possible numerically, because only in very few cases you have the actual function and you can actually calculate this. And therefore, convolution is much, much easier in Fourier space. Yeah? Just remember this. If you do the Fourier transformation, you can read this basically at home, so you get the talk, yeah? But this is the most simple derivation. So here you have your hx prime is the convolution function. This whole thing here is the Fourier transformation of the convolution function. You do a couple of little mathematical tricks here, which are very easy and very simple and very easy to follow. And if you do this, it turns out at the very end, oh, the complex convolution in direct space is nothing else than the product of the two functions in Fourier space. And this is also how Topaz works. In Topaz, you can explicitly tell the program where you want to work, yeah, in Fourier space or in direct space. If you have a function, it's easy and fast to transfer these functions to Fourier space. Fast Fourier transformation is doing this in incredibly short amount of time. If you do these two functions you want to convolute, yeah, then in Fourier space you just have to multiply these two functions, and then you do the back transformation, then you have your function you want. Yeah, just keep this in mind. This is actually how Topaz works in many instances. Yeah? So remember, convolution in Fourier space is much easier, and it depends on the conditions to do it either in complex numerically in real space or to do the whole thing in Fourier space. What else do we need? So we are almost through, yeah? So I taught you a little bit. When you do powder diffraction, you have to remember what the Dirac delta function is. The Dirac delta function is the function which is only defined by its properties. And it's a simple function, yeah? So we don't know exactly how the shape of this function is. It's not defined. But what defined is, if you integrate the function, let's say from minus infinity to plus infinity, it will be 1, okay? And what also is defined, if you multiply the Dirac delta function by another function, yeah? And if you do the integral, then what comes out is that particular other function at the position x0, okay? So typically, people say Dirac delta function could be a Gaussian function. But then Gaussian function, which is smaller and smaller and smaller and smaller and smaller, if it's smaller and smaller and smaller, it gets higher and higher and higher and higher. Basically, it's so small you can't see it anymore. It's extremely high, but if you integrate it, the result is 1. And why do we need this function? We need this function actually for so many things, in particular in powder diffraction, but in general crystallography. One is to point to a particular atom. The other is just to, as Rosanna mentioned today, just to describe a mathematical lattice, because this is the function which we can use to describe a mathematical lattice, and this is given down here. This is just a 3D sum of delta functions. So A, B, and C are the lattice parameters, yeah, and these are 3 delta functions, and this is going from 0 to NA. NA is the number of unit cells in A direction, and B is the number of unit cells in B direction, and NC is the number of unit cells in C direction. And this function called lattice function is G, which is the function which describes a mathematical lattice. Yeah? Again, nature is not making lattices. We make our life simpler by dividing, by taking out the content of one unit cell and having this infinite mathematical lattice here, and then just convoluting these two, which gives our crystal structure. Okay? Okay, now we start simple, or a little simpler. Position of a Bragg reflection. I think almost everything has been said this morning. Just to remind you how you do the calculations, very easy. You need a Bragg equation. Yeah. So this is a Bragg equation here. I don't repeat it again. It's just a little bit more complex here, because in the normal books, usually there's one atom in the first layer here, and the second atom is exactly below, which is of course not the real case. Yeah, it could be shifted. But then, of course, of the periodicity of the lattice, the next one has to be shifted the same amount, and the same amount, and the same amount, the same amount, the same amount, and so on. But they are not directly underneath. But if you do the calculation, you have a couple of more angles. But finally, this is the good news, it comes out the Bragg equation, which is given here. The, lambda is 2d HKL times sine theta. So what's in the Rietveld formula? And you see the whole thing gets complicated, because what do we have to put in here? We have a 2 theta HKL, yeah, a particular one of a particular reflection, the position of a peak. So we take it from the Bragg equation, yeah, and then of course there is some correction function. And the correction function can be just a 0-point error of your instrument. But it could be more complicated. Down here we have what Rosanna mentioned. We have actually the sample height error. And the sample height error is not linear. Yeah? You have a cosine factor in it. If you have a capillary which is not very well aligned, which is, let's say, misaligned in x and y direction, yeah? And if it's focusing geometry, it's not completely parallel geometry, then this matters. And therefore you have a more complex with 2 sine cosine functions combined. Yeah. If you use, for example, if you use Berns data, right? Yes. There's a complex small correction in it, which is also could be a quite complicated thing. It's a typically polynomial of second or third order, which you have to apply to your peak positions. Yeah. So you get it once from the lanthanum hexaboride, and then that's your function, and then this is applied to all the data. Yeah. So that can be complicated. You see, in this case, there would be 3 parameters plus the 6 parameters of your lattice, and the formula, the most general formula for the d spacing here, which goes in here, yeah, is here, and you see this is a complex formula. So all these things combined just go in the Rietveld formula just to determine the peak position. And these are all parameters which can be subjected to refinement, because you want to have the perfect values for your lattice and maybe also for the aberration of your instrument. Yeah? And then it's clear that if this is just one tiny little equation in the Rietveld equation out of maybe 20 we are using, yeah, then the whole formula cannot be analytical anymore. Okay? Okay, going to the intensity. The intensity we learned today also a lot, so I think I can do this fast. So it must be clear where the intensity comes from. In real space, we have the electron density. Yeah? So if we use X-rays, yeah? If we use neutrons, it's a little bit different, but here we restrict ourselves to X-rays. So we have the density of our atom. If we do the Fourier transform of the density of a single atom, yeah, we get, of course, our form factor, F. And Rosanna also showed a couple of pictures here are typically form factors as a function of sine theta over lambda for different elements. And the nice thing is they're normalized, so in direct direction, so if there's no diffraction, just a direct beam, so the scattering power, because all the electrons are in phase, right? So the scattering power is normalized to the number of electrons. So with some confidence, we have maybe a chance to say, oh, this is probably carbon and this is probably lead. It turns out to be a difference if it's carbon, oxygen, or nitrogen, because that is a problem, it's powder diffraction. All right, let's go on further. Life is more complicated. A good Rietveld program has to take the anomalous dispersion, anomalous scattering into account. And so the form factor is not just the form factor I've shown you before, the F0. It's also a delta prime and an imaginary delta I prime. okay? And you see here is a schematic, so the form factor F0 is this one here. Then the F prime is real, so it's just decreasing the scattering power. And the delta F prime is also reducing the scattering power. Actually, in some cases, it's even increasing it, so it's very rare. But it's usually decreasing, but it also has a phase shift in it, okay? So that makes it a bit more complicated, and things are here. But these things are usually coded in the Rietveld programs, like Topaz, for example. So now we have the electron density. We had the electron density of a single atom. So how does it work for the unit cell? And in the unit cell, of course, what we can do is we can actually sum up all the densities, which are point densities, because we say that there's a mathematical reason why we allow, or a physical reason we're allowed to do it. So we actually replace the entire atom by a single density here, yeah, and we fold it just with a delta function. And the only purpose of this delta function actually is to point from the origin of the unit cell to that particular atom, okay? And if you do this here in Fourier space, this is what comes out. And if you do this in the cell, you probably have seen this before. This is nothing else than the structure factor, right? So what comes out is the scattering, the form factor of the atom times the e to 2 pi I as x, which is the complex phase factor, and the sum gives you the structure factor. Okay, here it's shown again. So this is just the pointer, and this is actually the content of the entire unit cell. And now, as has been mentioned at least 3 times today already, yeah, we have this idea of the empty lattice. Yeah, we have a lattice of mathematical points. We have a lattice function, and we have the cell content, the content of one of these. And if we convolute them, so it's a convolution, yeah, we get our entire crystal. And now you will ask, oh my God, why he's telling us? We know this already. Yeah, because between single crystals and powders, yeah, we have to be aware that the lattice is small enough that there is an effect coming actually from the lattice. Okay, and this is given here. So when we have our lattice function, which we derived before, again here as a 3-dimensional lattice function, if we do the Fourier transformation, yeah, we get this function here, which is well known. If you square this capital G function, it's the so-called Laue function. Okay, but it's just a word. But you see, what comes out from here is that the great thing is that all the information in reciprocal space, in diffraction space, is located on these reciprocal lattice points. And if we have a huge number of lattice points, then this function, this Fourier transform function, becomes 1. And if you multiply 1 by something, it's not changing. But if it's smaller, it's not 1. That means you distribute intensity over the reciprocal lattice point. It gets diffuse. Yeah, and I think we have it here. So the density as a so this is the final one. The density of a unit cell as a convolution, given here. So this is for the entire crystal. Yeah. So if you look at the density of the crystal, we have to convolute the density of a unit cell with the lattice function, and in Fourier space, it's the structure factor multiplied by this transformed lattice function. Okay. Just to keep this in mind, that this plays a role in powder diffraction. Okay. All right. We also have seen, unfortunately, we don't measure the structure factor. The structure factor is the structure amplitude. Yeah? And unfortunately, in the structural amplitude, in these little x mu here of the different atoms mu, you see there's the position of the atoms. And it would be great if we would measure the structure factor, if we would measure the amplitude, we could relatively easy get the positions out of this. But unfortunately, what we see if we do diffraction is not the amplitude, is the modulus of the amplitude squared. Yeah, or in other words, it's the complex amplitude multiplied by the inverse, by the conjugate complex, yeah, which is given down here. And therefore, this information gets lost. And so all crystallography since more than 100 years try to recover this information. Yeah? This is known as the phase problem in crystallography, which is the same for single crystals and powders. But in single crystals, you have an overdetermined system. You have maybe 2,000 reflections. So there are lots of statistical methods actually to recover the phases. Once you have the phases, you get the X, Y, Z. In powder, this becomes more complicated. All right, just to show you quickly that things are, that the X, Y, Z are really in here, so you can actually use the F calc, the structure factor. You can divide it in A and B, so on the real part, which is, oops, this is here, and the complex part, which is here. So this is all known, but if you now apply the anomalous scattering, the formulas get big. This is the only thing I want to show you. I want to show you that this simple formula already is complex. You have seen how complex it was already for the position of the peaks. Now also for the intensity of the peaks without any corrections. This is the formula, for example, which is in topaz, yeah? Taking the anomalous scattering part into account, which is relatively complex. And maybe one thing, I think this is important to just to remember. I always, there's often the question from students, say, hey, when there's a powder, this is not one crystal, right? These are millions of crystals. And let's assume in our, what was the example? I think 7 million crystals, 7 million crystallites. Maybe 1,000 of these are in reflection conditions, but they are in different locations. So you would expect saying, okay, each one reflects, each one gives a diffracted intensities, but they're all separated in space, even if it's only 1 millimeter. That would mean the peaks are very broad, but the peaks are not broad. And the reason is very simple, because diffraction is a Fourier transformation. And the great thing about Fourier transformation is if you have Fourier transformation of the same object which are shifted by a shift in origin, yeah, so that means there's one grain, there's the other grain, you can say there's a shift in origin. This gives a shift in phase factor, but if you square the phase factor, it's 1, so it disappears. That's why we always get the same diffraction spot. The story is different if we would have the powder here and we would move the X-ray tube, yeah, then we would get many patterns overlay. But if the X-ray tube is fixed, yeah, the powder, no matter where it hits the powder, it reflects to the same spot in certain ranges, okay? Good. All right, so now we come to all these corrections. What has to be taken account in the Rietveld refinement, yeah, or in calculating a powder intensity. We have the multiplicity of a Bragg reflection. The easiest is, of course, when you have a cube and it's cubic, then you know the 100 as the same distance as the 001, as the 010, 00, minus 1. So there are 6 phases. The d-spacing is 6 times the same. And the good news is the intensity of all these 6 diffraction lines is the same. Therefore, yeah, we can say, oh, because for pure geometrical reasons, we have to multiply, or we have to divide this intensity by 6 to get the intensity of a single one. So the multiplicity must be taken into account. It's the minimum, of course, is 2. The reason is simple, because we have a lattice, and a reciprocal lattice. The intrinsic symmetry of every lattice is centrosymmetric. You cannot make a 3D lattice which is not centrosymmetric. That means you always have the HKL and the minus H minus K minus L are the same intensity, and therefore the minimum multiplicity is 2. Yeah, and the maximum, I think this is some strange cubic stuff, is 48. What else has to be taken into account? We mentioned this already. This is the Lorentz and polarization factor. Again, the multiplicity, the program takes care of it. Okay, once the units, the space group is correct, Yeah, the program will do this for you. The same actually for the Lorentz and the polarization factor. I don't want to go into too much details. I mean, the Lorentz factor basically has several components. Yeah, one component is that the Ewald sphere has a certain thickness. So depending on what angle the reciprocal lattice point moves through, it's either longer, or we can say yeah, it's or in the spherical shell, or shorter, and therefore this increases or decreases intensity. So program takes care of it. The big problem is what function you're using. I think this has been now fixed in Topaz. The general function you see down here is that there is the general sine theta of whatever position it is multiplied by the sine theta of the particular peak. Yeah. And usually people just say it's 1 over sine theta squared, sine theta 0 squared. That is perfectly fine. It's basically the same for sharp peaks, but if you have nanocrystalline peaks which go over the entire powder pattern, yeah, you get an asymmetry and you get a small shift. It's actually shown here. But this has been taken now care of. And the polarization is also important. You have to know if you're using a primary beam monochromator, if you use a secondary beam monochromator, no monochromator at all. Big problem if you use Goebel mirrors. Yeah, not everybody knows exactly what's the correct polarization correction for these. Yeah, but in general there are values given by the manufacturer, or you can calculate them by yourself. But you have to make sure you put in the right number. Yeah, there are lists and tables of this. Just don't forget this. Absorption. We heard a lot about the problem of absorption, and absorption in general is easy. It's just the Lambert-Beer law, right? Yeah, you all remember from school this nice experiment where you have your cuvette with some colored liquid in it, and then you have a laser coming in, and the laser has less intensity. Yeah, the thicker the whole thing is, or the darker the liquid is. Yeah, so that means it depends on the material and depends on the thickness. The same is in powders, and you would say, oh, it's easy. Yeah, in particular for capillaries, we can easily calculate this. It's just this nice function, but depending on the geometry, it turns out to be quite complicated. Yeah, so if you have thin flat plate transmission geometry, what you often use, so you have your powder patterns between two Kapton foils, yeah, and a very thin layer of powder, two Kapton foils. It's rotating like this to get a little bit of preferred orientation. You're shooting through, so it's basically a transmission technique. You see, depending on how the X-ray beam goes in, the correction functions for the absorption are entirely different. The same is actually for the Bragg-Montano geometry, if it's symmetric or asymmetric reflection, and for the Debye-Scherrer geometry. And you can easily imagine what it means in a Debye-Scherrer in a capillary. If you have, let's say, a strong absorbing material in the capillary, this is your capillary, the beam comes in. Yeah, at very low angle, the beam has to penetrate the entire capillary, so there's a lot of absorption. If you go to higher angles, even let's say backscattering, then the outer rims of your capillary, outer parts of the powder actually scatter back, so there's much less absorption. So the absorption actually decreases with increasing angle. If you don't take this into account, yeah, if you don't have the chance to use high energy, yeah, then you have a problem in quantitative phase analysis or structure determination. Debye-Waller factor, I don't want to say too much about. This is actually the picture of one of the many Mathematica scripts we included, yeah, in these papers, right? So you can you can see how it works, isotropic or anisotropic, how the displacement parameters work. You can click on these different points and see if you make it anisotropic. Put it this way: if you make your Debye-Waller factor anisotropic, you can easily fit an elephant, right? So for powders, you're only allowed to do this under very special circumstances. Let's say if you have, what's a typical example? If you have rotating little crystals like triflates, yeah, which are highly anisotropic, or if you have an extremely polarizable rubidium atom big and a couple of carbon atoms, then it makes sense to refine them anisotropically. But usually it's too dangerous. You get a good fit, but it's meaningless. So in powders, I would say it's already a challenge to get individual atom displacement factors. Okay, usually, and in particular for quantitative phase analysis, if you start refining the Debye-Waller factors, it always ends up in a catastrophe because you get a much nicer fit. So great difference curve, but your quantification is nuts. Okay. As long as you're not in the range, let's say 0.5 to 0.8 or something B, something like that. Okay, we have seen the TDS before, so Paolo showed this, I can go through it. Now comes also for all these corrections. We heard about preferred orientation. There are many, many things you can do actually to describe this, and one is, of course, you can use symmetry adapted spherical harmonics, which are very, very powerful. But here again is the problem. A spherical harmonic of 0 order, of course, is a sphere. It's the same in all directions of reciprocal space. If you go to 2nd order, it already becomes quite flexible. If you go to 8th order, you again can refine an elephant. So be very, very careful on using spherical harmonics. There's another example here. We can skip over this. Overspill is another problem in Bragg-Montano geometry. Just to give you an idea how many complex correction functions there are, and you have to carefully choose them. Overspill means if you have your sample container and your X-ray at very low angles, it's diverging, so the whole thing is overspilling the sample. So the scattering volume is not the same anymore. It's a different story when you go to high angle, then the beam becomes much smaller, and then of course this works. But you have to correct for this in case you take the intensities into account below the critical angle. Typically 7, 8, 9 degrees to theta, depending on your instrument. And you see the function gets more complicated if the beam is divergent. So there gets a couple of sine functions in it. Let's look a little bit about the time. It's okay, it's fine. Okay, now we come to the profile, and this is where we will do tomorrow a lot of little exercises in determining the instrumental resolution function. Why is the profile so important? The profile is important because this is now the best example of how important convolutions are. We have already seen from Klug and Alexander, we have seen these pictures. This is a famous picture. You have the convolution of so many effects for the final profile. So the final profile is a convolution between your instrument, or lots of aberrations from your instrument, typically optical elements or mechanical elements, and the microstructure of your sample. And typical features are here, let's say, the target function, the slit width could be divergence slit, could be receiving slit, the horizontal divergence, the axial divergence. Remember, we have Bragg cones, so what we measure is the rings, and if we have a very small ring and the detector has a finite size, the detector will see the ring well before actually there's the maximum, so the intensity will go up, and once it's behind, it will fall down, which is the main reason for the axial divergence. If you have a big ring, it's like this, that doesn't play a role anymore. So what are the two ways to determine the instrumental resolution function for Rietveld or for structure determination? One is the fundamental parameters, so we will do actually both. I mentioned this already. This means you either look in the manufacturer's manual and look at the different values for your instrument. How wide is my slit? How long is the slit? What's the distance between the sample and the divergence slit? What's the distance between the sample and the receiving slit? If it's no receiving slit, it's the slits of your silicon strip detector, right? They act as the same actually, and so on. So there are many geometrical things. You can either take a ruler and measure them by yourself, or you look in a manual, hope the values are correct. You can type them in, and then there's a couple of functions which try to mimic the physics, which try to mimic what effect this particular element has. It's easy for a slit because a slit is a rectangular function. Yeah, so that's quite simple. Yeah, it's not so easy if it's solar slits, because the solar slits could be they could be parallel, or they could be even actually having some angle. If they have some angle, it gets more complex. So all the functions, you have to keep this in the back of your mind. All the functions work well to a certain point. Yeah, so you always have to refine them. It could be that your receiving slit refines, you know it's 0.1, but it refines to 0.11. Fine, because none of these functions is perfect. Yeah, we are physicists. We are mimicking nature. We try to describe nature with very simple functions, with a few parameters. If you put an infinite number of parameters, you can describe everything. But if you have only a limited number, and we have a very limited, yeah, it will be good. We accept at some points this is good, but it will never be perfect. The alternative is to describe the instrumental resolution functions to find the phenomenological function which works great. And in my opinion, the easiest to use phenomenological function is so-called pseudo-void functions. I mean, where is this coming from? I mean, we know already that some effects form a Gaussian peak shape. Other effects, like the Darwin width, for example, of your monochromator, form a Lorentzian peak shape. Yeah? And this problem already was known to Woldemar Voigt around 1800, whatever, 98 or so. He was looking at spectroscopic data at that time, no computers, nothing. And he wanted to describe the profile. And he said, oh, probably the best idea is, since I don't really know, there's no physics behind. Nobody's telling me why it should be this or that. Let's do the convolution of Gauss and Lorentz, and this is the Voigt function. The problem is the Voigt function, we'll see in a second, it's quite complex to calculate. In Topaz it's possible, it's fast enough. But since it was complex for a long time, people looked for functions which are as close as possible to the Voigt, and one of these functions is the Thomson-Cox-Hastings pseudo-Voigt function. When we look at a peak, we have to characterize it. And what are the typical things to characterize a peak? You want to actually know how broad is the peak. It's a very dangerous thing, because you have to subtract lots of apparatus things, yeah, if you really want to learn something right from the width of the peak. Yeah? So again, this must be deconvoluted. Yeah? So instrument must be deconvoluted. But once it's deconvoluted, we have these typical values like the half width. Yeah. So the half width at half maximum is half the width of the peak at half of the height of the peak. And the full width, of course, is then 2 times. It's just the full width of the peak at half of the maximum. But you see, this is a problem, because this depends on the shape of the peak. Yeah? If the peak is more like this or that, this value varies. If you want information, a better way, at least physicists agree, so they're saying, oh, it's better to use the integral breadth. What is it? It's very easy. It's just taking the entire intensity of the peak, yeah, putting it into the rectangle, and the rectangle is as high as the maximum of the peak, and then the width of this rectangle actually is another measure which makes more sense to use, because it's more unrelated to the actual shape. Yeah? So when you report things like domain sizes or average domain size, it's better actually to report the IB value instead of the full width of maximum, or calculate the data from these values. All right. Just to give you an idea about the actual divergence, the smaller the angle, the more intense is the actual divergence, because the Debye rings, or the rings of the cones, get smaller and smaller and smaller. Yeah. But the size of your slit or of your detector is the same. So this is one thing. But also you see here, I measured in my lab, I have a couple of diffractometers. I have, for example, some copper, molybdenum, and silver K-alpha-1 diffractometers. I measured the same thing again. And you see, if you have divergent beam, then also the width of the peaks, yeah, the normalized width, the resolution depends on your wavelengths. If you go to the synchrotron and use pure parallel beam, it's independent. Yeah. Then the peaks get sharper, but then you re-normalize them to Q. Yeah. Q is not to theta. Yeah. To theta. Yeah. Is squeezed, but Q is of course the same. Then you will see that there is a very, very little change in the resolution. Yeah. Which is not the case in the laboratory. So you have to find the compromise what you're using. If you use molybdenum radiation, you have more power, you have more energy, you have less absorption. It's great. You can use strong absorbing materials in a capillary, but you sacrifice a little bit of the resolution. And this is just to give you an idea on the different functions which are used. For example, in topaz, I said a slit is usually described by a rectangular function. If you do the Fourier transform, because I said if it does how is it actually doing the convolution? So it's doing the convolution in Fourier space. It's actually this sinc function here in Fourier space. So this gives this sinc function in Fourier space. And you see this is a symmetric slit, so the Fourier transform is symmetric, so therefore it's only the real part. If you have a half slit, let's say you have some shape on one side, yeah, of course you have to take the imaginary part into account, so the function gets more complicated. Yeah? Where you're using this, you're using it, for example, here for tube tails. Yeah? So if you have two asymmetric rectangles at the bottom of the peaks to describe tails of the tube. Other functions which are used, for example, in topaz, they are relatively simple functions, which interestingly, when you Fourier transform, become quite complex. Yeah, so I did not put the formulas here, they get really complex. But again, in Fourier space, it's just a product. Yeah. So this is a circles function to describe a symmetry, usual actual divergence, a 1 over x function for other divergence, then an exponential function for transparency effects. Now we had this example of the transparency. So if you have a low absorbing powder and you put a kilogram in your sample holder, then the beam penetrates and penetrates and penetrates and reflects, and then you get this terrible shape, terrible asymmetric shape on the left side. Yeah. But of course, when you have the effect, you have to describe it somehow, to a certain extent. This is a typical Mathematica script. So when you download these scripts, you can play. Okay. You can, for example, put in the different effects and see, oh, how does the peak shape is affected in real space? How is it affected in Fourier space? How is it affected over the powder pattern and stuff like this? This is what we want to achieve tomorrow. This is just one example here. I'd probably use another powder pattern because I did this already 10 times, so I can't see it anymore. It's a beautiful powder pattern. Yeah, it's only four parameters to describe the entire powder pattern. It's a lab 6 profile. It's very high resolution recording. It's a Bruker molybdenum K-alpha-1 with a germanium 220 monochromator in the lynx eye. And you see, you only need the wavelengths distribution, yeah, which is some Lorentz function. You need the receiving slit, which is the head function. You need the asymmetry to the actual divergence, which is basically geometrically the source sample and slit length. And interestingly, because it's a position sensitive detector, which is flat, okay, but you are the focusing the circles in the diffractometer, of course, circles. So you have a circle at the flat detector, therefore you have a parallax effect, and this parallax effect is something like a tangent theta function. We will see this tomorrow. It's the same for all of them. Okay, let's see a little bit about time. So what I've got another quarter of an hour. Okay, I have to speed up a little bit. Okay. Because tomorrow we just want to do, I don't want to torture you anymore, we do tomorrow a nice presentation. Okay, about strain, so this is of course not an isotropic microstrain. What we mean when we talk about microstrain is delta D over D. Yeah? So it's a variation of the D spacing, yeah? Which is a measure for all kinds of defects. And the formulas, we don't have to go there. It's just a Bragg formula. You just do a full derivative of the Bragg equation, and then you come up with this beautiful simple function here, and you see the half width of your peak, if it's affected by strain, yeah, has a dependency on tangent theta, right? And when you do the same thing for the when you use the Scherrer, when you derive the Scherrer formula, I mean, the idea is very, very simple here, right? So you have the incoming beam reflected at your lattice plane, and now let's imagine you have a tiny, tiny little variation. So you're not in perfect reflection condition, yeah? You're moving a little bit away, and then you would say, oh, maybe, I mean, I still get almost constructive interference, so I should actually get broader and broader and broader peaks. But why do we get sharp peaks? Well, you all know the typical exam question, third or fourth semester. Of course, if you have, let's say, a little shift in the first plane, and you go lower, down, down, down to the next plane, then you find the plane deep in your crystal where actually the phase shift between the first and this one is exactly pi. It means it's extinct, yeah? And then the next one and the next one down there is pi, 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 so therefore you still have sharp peaks. But if this is not fulfilled anymore, if the crystal is too small in this direction, yeah, then of course you get the broadening. And when you do the calculation, so quite straightforward calculation here, yeah, you see, oh, the width of the peaks is not tangent theta dependent, but it's 1 over cosine theta dependent. This is the only reason why we can actually distinguish between the size of the domains. People say crystallite size, but it's not a crystallite, right? It's a coherently scattering domains. One crystallite could consist of 50 of these, okay? You're lucky if it's 1 to 1, but usually it's not, okay? But we get the size of the coherently scattering domains, yeah, because we can distinguish it from the strain because the dependency on 2 theta is different. But it's only different if we go out in 2 theta. The very beginning tangent theta and 1 over cosine theta are very close together. So we have to measure. You cannot stop measuring your powder pattern at 30 or 40 degrees. Okay, then you cannot get this information out. Okay, there's things like there's this shape factor in. It depends if it's a sphere, if it's a cube. Yeah, we don't know this. So what we get is the average size. Average over all shapes. If you're lucky, these are little spheres, but usually we are not. We just get an average size. And again, this width, the best is to use the integral breadth, not the full width that have maximum. This value is actually the more accepted one. So now we come to the phenomenological functions, the Voigt function. Again, we don't have to look at these formulas. I mean, this is, if you want to calculate the Voigt function, you see this is quite complex. This is the real part of the Faddeev function, of the error function here. In here is a very complex thing, which is not an analytical function, so you have to use approximations or tables. That's why people usually say, no Voigt, yeah. But I think Alan did a very good job, so he actually managed that the real Voigt is calculated very fast. And the reason is, since a couple of years, they're perfect approximation functions, which are so precise that you cannot distinguish them from the Voigt anymore. Okay, the Fourier space, the Fourier Voigt is actually much simpler, as you can see here, right? Yeah, so the delta here is nothing else than the width of the Lorentzian, the half width, and the sigma is the sigma of the Gaussian. So the Fourier transform Voigt function is actually a much simpler function, which makes it much easier, yeah, to do all the convolutions in Fourier space. Why is it so important that the convolution is correct? Very simple, because if you have two Lorentzian functions, and then the half width of these two functions is just the sum. If you have two Gaussian functions, yeah, FWHM Gaussian, so two half widths, full half widths that have maximum of the Gaussians, you cannot just add them. Yeah, you have to add the squares. So that means the full widths that have maximum of the resulting Gaussian is the square root of the squared sum of these. This means if we just add the Gaussian and the Lorentzian, it has absolutely no physical meaning. It it's not resembling a Voigt function. Yeah, it's too primitive. You can see it here. Here is just the width of the Gaussian is blue, yeah, and the width of the Lorentzian is red. And if I just sum them up, and therefore if I sum up any value between 0 and 1 of these two, it should always give me 1, no? A line. But the line we get from the Voigt is actually this curved green line here. Yeah? The dashed ones are the integral breadth. The solid ones are the full widths that have maximum. This is why it's so important to do this right. Yeah, to use a real Voigt or an approximation of the Voigt. And what we will use tomorrow is the double Voigt approach. So we convolute 4 Voigt functions. It's quite easy to do. And 2 Voigt functions are 1 over cosine theta. Yeah, we convolute 2 Voigt functions, and a Voigt consists of a Gauss and a Lorentz. So we have 2 Gauss and 2 Lorentz, and 1 Lorentz is the 1 over cosine theta dependence, the other Lorentz is the tangent theta dependence, and the same for the Gaussian ones. So these 4 are convoluted, and therefore we get something like the domain size parameters out of it. Yeah. Again, there's no physical reason why we use a Voigt. If somebody says, oh, because of the physics it must be a Voigt, it's wrong. We do it because it works. Right? All right, and this is how the parameterization of the Voigt function we are using, of the Thomson-Cox-Hastings, is working. And you can already see that the full width of half maximum has been approximated by a polynomial of 5th degrees. So this is all they did. Yeah, they actually fitted the mixing parameter, which is a mixing parameter between Gauss and Lorentz. So they say the pseudo-Voigt is a linear combination of the Lorentz plus of nu times Lorentz plus 1 minus nu times Gauss. So nu is a mixing parameter, and the mixing parameter is fitted by a polynomial of 3rd degree, and the full width of half maximum then is fitted by a polynomial of 5th degrees. And the dependency on 2 theta is this function. This people might recognize as the Cagliotti formula, which is known since the 1950s. It has been added some parameter here, set, and you see already why this has been added, because the Cagliotti function is actually the tangent theta dependence. So this is related somehow to strain. Okay? If I forget the V and the W actually I never use. Why? Because they're highly correlated, yeah, and they have absolutely no physical meaning. If I just have the square root of u times tangent squared theta, then I have square root of u times tangent theta. So square root of u has some relation to the strain for the Gaussian part. And the same is here for the Lorentzian part. It's the x times tangent theta. And therefore, one has added these 1 over cosine theta dependencies, the square root of z divided by the cosine 1 over cosine theta. Okay? So these parameters, so what we will refine is u, z, x, and y. This is the same approach as the double Voigt. We can either use the double Voigt, or we can use the pseudo-Voigt according to Thomson, Cox, and Hastings. Yeah? And we will refine tomorrow these 4 parameters. This is how it looks in the scripts. So again, if you're interested, if you have a mathematical license, it's a lot of fun actually seeing how the peak shape changes, what parameters have which effect, how is the half width changing, how is the domain size changing, and so on and so on. So you can use these sliders and you get a lot of information. Okay, coming to structure determination, and we can keep this pretty short. Do we have a few minutes? 8 minutes, wonderful. Because there's absolutely no reason in this world why we should do local minimization except for computing power. Okay? If we could, we would do all refinements in a global way. Forget about parameters being so close to the truth. Just say, hey, put all the parameters in. We have this global parameter space. This is 20 parameters, so 20 space. This is, I don't know, done in a minute. It's not done in a minute, because if you do it nowadays, it would be a couple of million years. with our computers. It's easy calculation. I could do the calculation here. I could show you. It takes a few million years to solve a moderately complex problem, actually a simple problem. So global optimization is a bigger problem, and people thought long about this. They said, hey, how can we simplify this? We do not want to do any grid searches. It doesn't make sense. But people figured out, it was particular here, this wonderful paper by Newsom, Deem, and Freeman in 1992. They had the idea and say, let's use a simulated annealing. So the idea is extremely simple. So what you do is, you fit the entire powder pattern, and as information, you take all the intensities you get, and from those intensities, where there is overlap, you have a factor which is describing the degree of overlap. In other words, if the two peaks overlap by more than whatever 90%, the two peaks are counted as one piece of information. As soon as they are a little bit more separated, they are counting as two, but with a less weight. And if you're completely separated, they have the full weight. Okay? So you have a list in the computer. There's a list of, let's say, 200 peaks from the powder pattern. Maybe 30 peaks are separated, and the 160 have a more or less degree of overlap. And from this, you can calculate actually, a chi-squared. You can call it an energy function. From the intensity, or even from the entire profile. Now we say the intensity, and you can say, okay, how good of a completely arbitrary structure, which I throw into my unit cell, how good do all these peaks as a sum fit together? And of course, it's terrible. Or you're lucky, one out of 100 billion. Found a structure, just one match. No, it's not working. So the computer puts it in, and then, of course, the computer is doing changes. It could change the x, y, z position. It could change the displacement factor. It could, if you have rigid bodies, it could rotate and translate rigid bodies, and so on, and so on, and so on. And then it's calculating a new chi-squared. And then it's comparing the old and the new chi-squared. If it's better, it's great. But if we only would do movements which lead to better ones, we would get stuck in local minima. And so the simulated annealing means you are allowed to jump over these little hills of energy. So it says, okay, it gets worse, but I still accept it, but with a lesser probability. And now it gets worse, where at some point the problem is, do something completely new. But very often it gets worse, and then it gets over one of the Himalaya mountains, right? And now you're in the valley which leads to the ocean, and then you can solve the structure. So this is the idea behind. So you accept bad moves with a certain probability, and the probability at the beginning of your structure solution is extremely high. That means you accept all moves. You just broke the space. Let's say you make 1 or 2 million trials in space, and then you pick up the best solution. From there, you start actually do moves, smaller moves, and you accept you accept the worth chi-squared with a lesser probability, and this probability is basically a Boltzmann function, and in the Boltzmann function there's a temperature, and therefore it's called simulated annealing. Okay, it's not a temperature; it's just a parameter T. But we call it temperature. Therefore it's called simulated annealing. It's like if you have molten metal, and the metal, if it's very hot, goes in all kinds of directions, the atoms, and when you cool it down, it will start actually shaking only a little bit, and if it's completely cooled down, it stops. And the same idea. The only problem is there's no guarantee that you find the solution. You will find the solution if you do this an infinite amount of times, and if you find the correct solution multiple times. But in general, we have chemical knowledge. We can look at structures. We can see if the structure makes chemical sense. So we get the feeling if it's probably right. There's no 100% guarantee, but it works actually pretty well. And I'm not going into this, but there are zillions of more complex algorithms attached to it. You can do so many things. Yeah. So the basic algorithm is pushed up a little bit with lots of mating in mutual change and genetic algorithm and I don't know what. Yeah. But the basic idea is the simulated annealing, which in my opinion works best. All right. You can reduce the number of degrees of freedom. We will do this tomorrow by rigid bodies. Very easy. If you have this is a CP star ring here. If you have a CP star ring, yeah, you can refine all the carbon atoms, which are 10 carbon atoms. Yeah, you can refine them individually. Then you have a huge number of parameters, and of course they all do meaningless changes. It's almost impossible to find the structure. But if you know that's a ring, you put in the chemical knowledge, and then the entire ring is more or less fixed, and you only have the rotations 3 and the translations 3, so 6 parameters. And maybe you let it breathe a little bit, yeah, in a general way, 1 more parameter, and that's much easier to do this. Let's see how we are doing. Just okay, good. Oh, maybe I need a few more, but then I'm done. Okay, this is how it works. Also in many programs, also Topaz. Yeah. So introducing chemical knowledge is actually changing the minimization function, because you also have to add minimization of the penalties. Yeah. And what you want is you want to sharpen your minimum. You don't want to force the system to go in a direction which is completely given by your model, okay? Yeah? In theory, you could say, oh, forget about the powder pattern, we just minimize all the penalties. Say, this cannot be closer than that one, this can only rotate this way, and so on, so on. And at the end of the day, yeah, you can solve the structure without having a powder pattern, but this is not the idea, yeah? So you want that the chi-squared surface, which is very shallow means many solutions look right. There's only one correct one, but the system from the powder pattern cannot distinguish if the carbon atoms here. But it could do this when it knows it's a rigid body. Then the rigid body will be more or less fixed here. Yeah. But the 5 carbon atoms, they can move a little bit around. Yeah. And this means your energy surface, your chi-squared surface, is getting sharper. Yeah. But you should not artificially change it. It should not be at a higher or much lower value. This is basically given here. This is something we do not do here, so I just mentioned this. We will not do this during the course, but one of the powers of powder diffraction, of course, of Rietveld is that we can refine many Rietveld patterns at once, which is absolutely cool. Yeah, so now when we now go home from the synchrotron, we maybe have 500 powder patterns as something, let's say something simple is a temperature series, yeah. And now you can say, okay, who is the PhD student I don't like at all? Okay, this guy, you do the 500 powder patterns until next week, yeah. And then he's sitting, he's doing one by one by one. It's terrible, huh? This is something a computer can do. The easiest way is sequential. You refine one pattern, and then you take the parameters of this refinement, give it to the next one, refine the next pattern automatically. Or you even say, oh, I know there's a the only thing which is changing is the thermal expansion. This is a function, a polynomial function of second or third degree. I just put in the polynomial function in. I don't refine the lattice parameters individually. I just refine all 200 powder patterns at once. And then I get the 3 values out I want, which is called parametric. So these things are possible, but as I said, not part of this. Okay, we don't do this. For the last 1 minute, just one example, because I have to show you at least one example, which is fun. I love this one. It has been solved by one of my former PhD students, Sebastian Bette. This is the adoration of the shepherds by Toretti. A very important piece with an interesting history. It was in the Byzantine Art Museum in Berlin. It's actually there again. There was a big fire. There was a bomb dropped on the Second World War. So there was a big fire. So it was burned, but it's an important piece. And the Russians came and they took a lot of art to Moscow. So they took the piece and it broke. And then they used some strange glue. They brought it to Moscow and they let it there for decades. And then there was a restoration program so that stolen art in all kinds of the world. Sometimes it works, sometimes not. So this worked, so they brought it back to the Byzantine Museum. And then, of course, the people restoring it had to get rid of this glue with some chemicals. And what happened is we had these efflorescence products here. These are, okay? And it turned out it was not so easy to figure this out. We found it out using the IWPD PDF 5 Plus database. We found out it's calcium acetate hemihydrate. As simple as it gets. Calcium acetate and half a water. That's the simplest structure in the world. But there was no structure in none of the databases, so we solved it from powders, because as you can see, this is a powder, right? It's a single crystal. And this is a powder pattern. It's so complex. It's a complex powder pattern, and it has 12,000 cubic angstroms. And when we finally solved it, we found out there are four different environments of four different acetates, yeah. And this is the structure, which is the first triple helix structure, or the first helix structure, I would say first triple helix structure like collagen, which is not from amino acids. Yeah, it's just the acetates. Extremely complex structure. I mean, the whole thing has actually a terrible story. So we wrote the paper, we submitted it, and the referees sent back and say, "Oh, cool structure, but we don't believe it." It's from powders. Powders cannot do this. It's impossible from powders. And so finally, we know Ute Kolb doing electron diffraction. We finally found the piece which we could use. We went to the electron microscope, electron diffraction. They solved the structure again, and it turned out to be exactly the same structure. Yeah, and so we have this combined paper, electron diffraction and powders. But I just want to show you, powder is very powerful. It's amazing what you nowadays can do with powders. And after the course, you hopefully are all specialists and can do these structured determinations. Yeah. All right, and tomorrow there's lots of exercises, no more formulas. Thank you.